Every movement you make, every breath you take, every flicker of light and rise in temperature traces back to a single idea. Energy never disappears, it only changes form. From the motion of planets to the warmth in your hands, energy links the visible and invisible workings of the universe. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Energy feels intuitive, yet for most of human history, its true nature remained hidden. Motion, heat, light, and electricity were once treated as separate phenomena. Only through centuries of observation, experimentation, and debate did science uncover a unifying principle. Energy is the common currency of change. Understanding how motion becomes heat reshaped physics, chemistry, biology, and modern technology. The earliest scientific ideas about energy emerged from motion. In ancient Greece during the 4th century BCE, Aristotle described motion as something requiring a continuous cause. Objects moved only while being pushed. This view dominated European thought for nearly 2,000 years. A major shift occurred in the 17th century. In 1638, in Italy, Galileo Galilei published two new sciences, laying foundations for the study of motion. Galileo demonstrated that objects accelerate uniformly under gravity, and that motion follows mathematical laws. His work set the stage for a deeper understanding of how motion stores and transfers power. In 1687 in England, Isaac Newton published Philosophiae Naturalis Principia Mathematica. Newton defined force, mass, and acceleration, revealing how motion changes when forces act. Though Newton did not use the modern term energy, his laws made it possible to quantify motion precisely. During the early 18th century, the concept of kinetic energy began to emerge. In Germany, Gottfried Wilhelm Leibniz proposed a quantity he called vis viva, or living force, proportional to mass and the square of velocity. Though controversial at the time, this idea closely matched what we now define as kinetic energy. Heat, however, remained mysterious. For centuries, heat was believed to be a substance called caloric that flowed from hot objects to cold ones. This theory dominated European science in the 18th century and appeared consistent with everyday experience. The caloric theory began to collapse in the 1790s in Munich. Count Rumford, born Benjamin Thompson in the American colonies and later working for the Bavarian government, studied the boring of cannons at an arsenal. He observed that friction during drilling produced seemingly endless heat. No matter how long the process continued, the heat never ran out. Rumford concluded that heat could not be a material substance. It was generated by motion. Friction converted mechanical work into heat. This observation marked a turning point in thermodynamics. Further evidence emerged in the 1840s in England. James Prescott Joule conducted careful experiments in Manchester, measuring how mechanical work produced heat. In his most famous setup, falling weights turned paddles submerged in water. As the paddles stirred the water, the temperature rose. Joule demonstrated a precise numerical relationship between work and heat. Mechanical energy and thermal energy were interchangeable. His results established the mechanical equivalent of heat and directly challenged the caloric theory. By the mid-19th century, energy had become a unifying concept. In 1847, German physicist Hermann von Helmholtz published On the Conservation of Force. Helmholtz argued that energy could change form but could not be created or destroyed. This principle became known as the law of conservation of energy. Thermodynamics soon followed. In France and Britain during the 1820s and 1840s, scientists such as Sadi Carnot and William Thomson, later known as Lord Kelvin, studied heat engines. Carnot showed that heat flows from hot to cold and that only part of it can be converted into work. This led to the second law of thermodynamics, which introduced the concept of entropy. While energy is conserved, its ability to do useful work decreases as it spreads into less organized forms, like heat. Motion, turning into heat, is now understood at the microscopic level. In solids, liquids, and gases, temperature reflects the motion of atoms and molecules. Faster motion means higher temperature. When friction slows down visible motion, that energy does not vanish. It becomes microscopic vibration. This principle applies everywhere. When a spacecraft re-enters Earth's atmosphere, its kinetic energy converts into heat through air resistance. In power plants, turbines convert motion into electrical energy, while waste heat escapes into the environment. In biology, energy transformation sustains life. Inside cells, chemical energy stored in molecules like glucose converts into motion, electrical signals, and heat. Muscles generate movement by converting chemical energy into mechanical work. The warmth of living bodies is a constant byproduct of energy transformation. During the 20th century, energy science expanded further. In 1905, Albert Einstein published his theory of special relativity in Switzerland, revealing that mass itself is a form of energy. His equation showed that enormous energy can be released from small amounts of matter. Nuclear reactions confirmed this principle. In the 1930s and 1940s, research in Europe and the United States demonstrated how nuclear fission converts mass into heat and radiation. Modern nuclear power plants rely on this transformation, turning atomic energy into thermal energy and then into electricity. Today, energy science governs climate research, renewable technology, and engineering. Solar panels convert light into electrical energy. Wind turbines convert atmospheric motion into power. All follow the same foundational rules uncovered over centuries, from falling stones to spinning galaxies, from burning fuel to warming skin. Energy flows continuously through different forms. Motion becomes heat. Heat drives motion. Nothing is lost. Everything transforms. The science of energy reveals a universe built on continuity rather than disappearance. Change does not destroy energy. It redistributes it. This understanding replaced older ideas of hidden substances with measurable laws that apply everywhere. Energy connects physics, chemistry, biology, and technology into a single framework. It explains why machines wear down, why living organisms need fuel, and why no system operates with perfect efficiency. Motion and heat are not separate forces. They are expressions of the same underlying reality, shaped by how energy moves through matter. This is Mattermosaic, piecing together the universe, one discovery at a time. If this deepened your sense of wonder, give it a like, pass it on to a fellow science fan, and tell us what topic you'd love to see next. Subscribe to join us for new discoveries every week.